So let's start by looking at the big picture here. We're talking about the radioactivity of the sample. We want it to drop below some threshold. So the equation we're going to be using in this problem is that the activity is equal to the initial activity minus lambda t. Okay? Now, we need to know now that we're told the final activity here, A, is 3.0 microcuries, right? Which is 3.0 times 10 to the minus 6 curies. Now I'm going to go ahead and convert that into MKS units. So I'm going to multiply by 3.7 times 10 to the 10th becquerels and divide by curie. All right, that gives us, let's see, 1.11 times 10 to the 5th becquerels. Okay? How about lambda? Let's do that next. Well, the half-life is given to be 5.27 years. Okay? Again, let's work in MKS units. So I'm going to multiply that by the number of seconds in a year, which is 1.66 times 10 to the 8th seconds. And then lambda is 0.693 divided by the half-life in seconds. That's 4.16 times 10 to the minus 9 decays per second. All right? Finally, let's get A naught. Let's figure out what that is. So the initial activity is equal to lambda times the initial number. So we can get the initial number because we've got the mass, right? The total mass of cobalt that's present is 2.5 grams, so it's 0.0025 kilograms. And the mass of an actual cobalt nucleus is, well, I guess 58.9332 AMU. And we know that the total mass is equal to the number of cobalts times the mass of cobalt. Okay, well, the number of cobalt atoms that's present originally, that's N naught. Okay, so the number of cobalt atoms is equal to the total mass divided by the mass of cobalt. Now, let's see. So the total mass, 0.0025 kilograms. The mass of cobalt is 58.9332 AMU, but see, I've got to convert that into kilograms. I want to have the top and the bottom in kilograms, so to do that conversion, I know that there's 1.66 times 10 to the minus 27 kilograms per AMU. So that'll convert this denominator into the proper units. All right, and if I do that, I get 2.56 times 10 to the 22nd. That's the number of atoms. Now, the initial activity is lambda times that initial number. So that's 4.16 times 10 to the minus 9 from up here. And then n is 2.56 times 10 to the 22nd. So that's 1.06 times 10 to the 14th. Okay, now I've got the initial activity, I've got the final activity, and I've got lambda. Okay, so my equation, A equals A naught e to the minus lambda t, is 1.11 times 10 to the 5th, from right here, equals 1.06 times 10 to the 14th, times e to the minus lambda t, where lambda is up here. Alright, so if I divide both sides by this, I get 1.04 times 10 to the minus 9 is equal to e to the minus lambda t. Now I take the natural log of both sides, and I get negative 20.7 is equal to minus lambda t. Now I'll go ahead and plug in lambda. That's 4.16 times 10 to the minus 9. I just didn't plug in lambda earlier because I'm too lazy to write it out that many times. Okay? So if I solve for t, I get 4.97 times 10 to the 9th seconds, which is 160 years. Okay, let's think about that for a minute. So has a half-life of 5.27 years, and it basically has to drop from an initial activity of 10 to the 14th down to 10 to the 5th. So it has to drop about 9 orders of magnitude. Each order of magnitude is about 3 half-lives or so, a little more than 3 half-lives. So 27, or maybe around 30 half-lives, and 30 times 5.27 years is in the neighborhood of 160. So that's ballpark. So that looks like a good answer.